I guess you might be struggling with the gateway topic of stoichiometry.
Sure.
Stoichiometry seems to be difficult until you understand two things. One, the mole concept, and two, how to work with proportion.
Okay.
In the next 3 movies, I want to help you to understand the first of these, the mole concept. In order to do that, in this movie, we deal with why we need the mole. That's very important to help you to understand the next movie, where we get into what the mole is. And then in the last movie, we'll close the circle by showing how the mole concept solves the problem, which made us need it in the first place. Before we get to that, click on the link below.
I can't see any link.
You need to view this in YouTube to see the link. You'll see that it opens up a self-marking quiz about the movie's topic. Complete the quiz while you watch or after you've watched to check your understanding and make the process more interactive. You'll also see a timeline of the topics that we deal with in this movie so that you can easily jump to places you need to rewatch. And while you're there, please like and subscribe and press the bell and check out my website, learnscience.coza. And to help me to produce more movies like this, you can support me on Patreon. Find the link below.
Okay, so why do we need the mole?
It's because we need a way of referring to how much that's appropriate for chemistry. And to understand that, we first need to understand different ways of referring to how much. Secondly, we need to understand submicroscopic and macroscopic forms of representation in chemistry. Then thirdly, we need to understand the problem that the mole concept solves.
What is this problem?
Very briefly, this problem is that practically we work with macroscopic quantities of chemicals, and for them we can't measure how much is how many because the particles of chemicals, atoms, ions, molecules, are too small and too numerous to count. We rather use a variable like mass, which we can measure. But conceptually, we don't think about macroscopic quantities, but rather about submicroscopic particles. And it's impossible to measure their mass because they're too small and light. Instead, for them, it's best to work with how many as how much. The mole concept solves this mismatch because it provides the link between the practical macroscopic and the conceptual submicroscopic.
Now that was a mouthful.
Well, don't worry if that doesn't make 100% sense to you just yet. Hopefully by the end of the movie, it will. So, let's dive in to why we need the mole concept. First, what does how much mean?
It means how much?
Well, yes, but there are many ways to describe how much. Let's start by using money. Let's say we have 2 Rand coins. How can we describe how much we have?
8 Rand.
There are different ways, each way best suited for a particular purpose. We might give the total value of the coins because that tells us how much we have to spend. But let's say that there was some kind of machine which took 2 Rand coins, maybe to play a game. Then it would be more useful to count the coins and express how much we have in terms of how many we have.
Oh.
And that tells us how many times we can play the game. And then, of course, there's a third way. We can measure the mass of the coins, and that can be useful if we go to the bank with a big bag of 2 Rand coins. And then instead of the bank teller having to count the coins, they can instead weigh the whole bag.
55 grams.
And because they know the mass of 1 2 Rand
5,5 grams.
from that, they can calculate how many there are inside.
55 grams divided by 5,5 grams equals 10 coins.
To help us to understand how that's related to chemistry, let's now step away from the issue of how much just for a moment. And before we return to it, we first need to understand macroscopic and submicroscopic forms of representation in chemistry. If I say water, what do you think about?
What? water!
Yes, you probably think about a liquid that we need for life. Maybe you also think about ice or water vapor. Those are macroscopic forms in which we experience water. Macro means large, and scopic means how we view things. So macroscopic forms of water refer to forms on a large scale which we might be able to view with the naked eye. We can measure out a certain mass of liquid water or of ice using a mass scale. And so an easy way to represent how much with macroscopic quantities is through mass. It's useful practically to work with chemicals on the macroscopic scale because that's the level at which we actually work with chemicals in real life. So a variable like mass has practical value. Let's go back to my question. What do you think when I say the word water?
H2O?
2 hydrogen atoms covalently bonded to an oxygen atom forming a water molecule. That's a submicroscopic representation of water.
Sub means smaller than? Smaller than a microscope?
Submicroscopic refers to something smaller than what can be seen under a microscope.
Okay, that's not what I see here.
It refers to models of atoms and molecules. These submicroscopic models are useful to help us to understand what happens during chemical reactions. So we can say that submicroscopic models have conceptual value. What's the easiest way to measure how much on the submicroscopic level? I guess I could count the atoms or the molecules and then tell you how many there were. Exactly. So now we get to an issue which is crucial if you want to understand the concept of the mole.
What is it?
The problem which the mole concept solves. The mismatch between the practical way of measuring how much on the macroscopic level, how heavy,
Mass?
and the conceptual way of describing how much on the submicroscopic level, how many, counting particles. But could you maybe use an example to help me understand that? Let's say we work for SpaceX, planning the next rocket launch to space. We need to describe how much hydrogen and oxygen we must put into the rocket. You see, hydrogen and oxygen are cooled and pressurized until they liquefy, and that liquid hydrogen and oxygen are measured out and placed in the rocket. Then during the launch, they react explosively with one another to form water and a lot of energy, and that energy is what pushes the rocket up. Okay, so we could weigh the amount of liquid hydrogen and liquid oxygen that we need, and then we could say how many grams that is, or kilograms. Yes, that's a practical way of expressing how much, because it's a macroscopic measurement. We can take an observable amount of the chemical and put it on a scale and see a reading. But that's not the only way to describe how much we have and how much we need. And when we start thinking about what's happening and how much we need, it's actually not the best way. Rather, it's better first to think about relative numbers of submicroscopic particles.
Okay, to think about H2O.
We know that the hydrogen,
H2,
and oxygen,
O2,
consist of submicroscopic diatomic molecules. And when hydrogen and oxygen react, the atoms in the molecules separate and then recombine to form water molecules of formula H2O. And what does that tell you about how many hydrogen atoms we need compared to oxygen atoms?
2 H's for every 1 O?
Yes. We need twice as many hydrogen atoms as oxygen atoms so that there won't be any unreacted reactants left over at the end. But now we have a problem.
What is it?
The practical macroscopic way of measuring amount as mass doesn't work out as simply as what I've just described may seem.
Okay,
Do you mean it's wrong to say we need 2 grams of hydrogen for 1 gram of oxygen? Exactly. But why is that wrong? Because how many and how heavy are not the same thing. And because hydrogen and oxygen atoms do not have the same mass as one another. Okay, so how are we meant to know how much hydrogen and oxygen to weigh out, to put in our rocket? We want double as many hydrogen atoms as oxygen atoms, but that doesn't help. Because we can't go count them. They're too small. We need to weigh them. But that's not the same thing. So what do we do? Exactly. We have a disconnect between the way we think about how much on the submicroscopic level, how many, and the way we actually practically measure out how much on the macroscopic scale. For example, how heavy? Yes. How do we link these two ways of describing how much so that we can translate what we know conceptually on the submicroscopic level to what we must do practically on the macroscopic level? So, get on with it. How? The mole concept provides this link. And so the mole concept solves this problem. How? Well, you're just going to have to watch the next movie. First, a quick recap. In this movie, we looked at different ways of referring to how much. For example, particle counts, how many, and mass, how heavy. We looked at the differences between submicroscopic particles and macroscopic quantities. We did this so that we could understand why we need the mole concept. We need a way of referring to how much that bridges the gap between the way we think about chemicals submicroscopically, where how much is best thought of as how many, and the way we practically work with chemicals macroscopically, where how heavy is a better way of expressing how much. The mole concept bridges this gap, so don't forget to watch the next movie about what the mole is. Don't forget to like and to subscribe. Let's do this together. Let's learn science.